Hello everyone, this is a video presentation for my paper M2M communication system for network robots with low memory footprint. First of all, I would like to brief you about three scenarios for M2M communication. Scenario 1 is where a robot directly communicates with another robot to which it wants to communicate. In this, the message is directly transferred from the sender to the intended receiver. Scenario 2, where a robot passes its information to another robot and that robot passes it to another robot till the message reaches its intended receiver. This can be seen with gossip algorithm. The third scenario is where a robot wants to communicate but there is no other robot in its communication range. So to reach any other robot, it has to explore its environment. But if it detects any other robot, it can pass its information and we get back to either scenario 1, that is direct transfer, or scenario 2, that is gossip algorithm. So to explore the environment, we have proposed the use of rapidly exploring random tree. In this, the robot, say it is present at point M1, it chooses a random point M2. From M2, the nearest point with where the robot ever situated in its past history is chosen. Say in this case it is M1, since it is the only point. So from M1 to M2, the robot travels a distance L, which is M3. So the new node is M3. Likewise, we have proposed an RRT forward propagation system. In this system, we have 3 steps for traversing or exploring the arena or the environment. Say the robot starts its exploring from a point M1. The robot randomly chooses a point M2. The nearest node from M2 is M1 since it's the initial position. So the robot moves to a point M3 which is at a distance of L in a direction of M2. So the new location of the robot is M3. Again, a new node is selected, a new random position is selected, that is M4. The nearest node from M4 is chosen, that is either M1 or M3. So in this case it is M3. So the robot moves to M5, which is at a distance of L in a direction of M4 from M3. So the new current location becomes M5 in step 3. A new random node is selected, that is M6. The nearest node is chosen. In this case, from M1, M3 and M5 it is M1. So the robot moves from M5 to M1, then moves from M1 to M7, which is at a distance of L from M1 to M6. So the final position of the robot becomes M7. So the robot's current position and its previous nodes is saved in RRT buffer. You can see it here. And the nearest nodes to the current positions are saved in another column. You can see it is here. These 2 columns help the robot to move from one node to another. Now for the exploration part, here is the abstract model of our proposed communication system. First of all, the robot senses the environment. If another robot is found which had its pain lower than the transmitting robot, then the transmission is done and the message is sent. if C or C and W, that is communication pain and work pain, is greater of the receiver's robot than the sender robot, no transmission is done, and this robot then go for exploration or the exploration of its physical environment. If any robot is found, it again do the comparison of C and W and selects whether a transmission can be done or not. So this cycles occurs till the robots C or W both becomes 0. If the sender robots C and W, that is communication pain and work pain, is both 0, it means the robot has nothing to do, it has neither to communicate nor to do any work, so it becomes an idle robot. The whole backbone architecture can be seen in the paper like this. So we have used a modified gossip algorithm. We use a modified version. If two nodes are within communication range, we say that they are neighbors. When a robot wants to send a message to a destination robot, it randomly chooses one of its neighbor and transmits the message together with a header that contains the identifier of the destination and itself, and a time value indicating the validity period of the message. So if a message is hopped too many times, it will die. Modification reduces load on robot and reduces delay. Packet is forwarded only when the pain of receiving robot in terms of W and C is less than the pain of sending robot. F depends on the equivalent pain of both the participating robot, XR and XS, where XR is the receiving robot and XS is the sending robot. The overall pain of any robot, say X, is a weighted sum of its W, that is working load, and C, that is communication load, or we can say working pain or communication pain. Alpha and beta are the predefined weights of W and C, which depend upon the task being performed by the robot. So here is the header. We have source address, destination address, sender's address, and pain W and pain C, and also the time to live. And the other header information are used for communication protocols, and the last part is the message data that has to be transferred. Now for the idle robot protocol, idle robot has both pain W and C equal to 0. We have already seen it in the abstract diagram. These idle robots can be used to improve the communication reach of the network. They can be placed in location where very idle robot protocol. When no robot is found in the communication range, the robot traverses in the environment randomly. If it comes in the communication range of any one of the robot, say R1, it moves to the periphery of the communication range of R1, so that the overall communication range of R1 increases. It can be seen in the diagram that the overall communication range of R1 increases from R1 to the communication range of I, that is idle robot. Say if any other robot R2 comes in the communication range of I, that is idle robot, it automatically comes in the communication range of R1. So the overall communication range can be seen to be increased. In this scenario, the idle robot goes to the periphery of the whole network, that is R1 and R2, and hence the communication range of the robot system R1 R2 is effectively increased. Now simulation results. The simulation result for RRT forward and RRT backward propagation can be seen in this diagram, that on increasing the population size n, that is the number of robots used in an environment, the average computation time of overall system increase linearly. We can see the slope is almost constant. So the computation time per robot on increasing the size of the system doesn't change. So it is computationally efficient even on increasing the population size. Now the future aspects. The pain-based structure can be improved by using motivated learning cognitive architecture, but for this the memory size has to be increased. The use of cognition in this system can help us study the behavior of a swarm in unknown environments. If the computation and the memory is not a restriction, the use of SLAM can also be done. In this, the exploration can be improved. And that's all. Thank you. For any queries, you can contact me on abhishekjha2010@gmail.com. Thank you.